So good day, sir. This is Team 2 here to explain about B trees and KD trees. B trees will be explained by me, Anish, and KD trees will be explained by Aishwarya. So let me get into the topic. The agenda we have is introduction, code link, an overview of B trees and KD trees, implementation, comparison, and real life applications. So let me first talk about what is B trees. B trees was already taught in class by Subin sir. So basically, B trees is used to store big data structures. Not big data structures, big datas, and it is used to efficiently access and retrieve them because it has a time complexity of O of log n for most of the operations. So when we get into the definition of B trees, we have it like B trees are self-balancing data structures that maintain data in a sorted manner. They are designed to efficiently manage large amounts of data. And the node structure here has multiple keys and child pointers. The key operations what we have used here is insertion, deletion, search, and display. Yeah. So let me get into the topics here. The functions we have used here is obviously written here: insertion, deletion, search, and display. But we have a lot of other helper functions which is mentioned here. For insertion, we have split child and insert new. For deletion, the helper functions are borrow left, borrow right, merge nodes, get pred, get successor, and we have search and display functions. So let me get into the algorithm of each functions here. So for the split child, we have create a new node to store the right half of the keys and the children of node y, move the appropriate keys and children from y to z, and update the contents. So basically, let me show how average B tree would look like. This is a B tree which has 3 children and 2 keys. So basically, keys and children here specify the number of nodes and childrens. So according to our code, we are getting an input from the user called t, which means it is the key where the number of keys in this B trees would be 2t, number of children would be 2t, and the number of keys would be 2t minus 1. We did this because we weren't able to think up an algorithm which would efficiently choose the best number for median when the number of keys are 4 or any other even number in order to accommodate the median properly. And the rest is yeah, so we've used it like 2t as the number of children and 2t minus 1 as number of keys. And the next one is delete function. For delete function, if there is a child to the left and there is no child to the right, accommodate the child to the left and update the tree as per the order, and same for the right as well. So let me talk about the time complexity analysis for B trees, which was done by me. The insertion operation here is O of log n, but if there is any other additional splitting or merging, that would also accommodate another time complexity of O of log n. For deletion operation is the same O of log n, but again we might encounter merging or redistribution of nodes, which may take another time complexity of O of log n. The search operation is also O of log n. We could see that the basic operations such as insert, deletion, and search take O of log n. This is the best scenario for this tree, as it is used a lot in data structures in order to store a large amounts of data. It wouldn't impact us a lot if we use small amounts of data, but whenever we encounter large sets of millions or billions of data, this log n would be very much significantly or exponentially faster as compared to O of n. So the display here is O of n again here, because whenever we use in order or pre-order or any other kind of traversal, we will have to search every other node, so it would be O of n. For the space complexity for the same, the node storage would take O of n, as obviously we'll have to store n number of nodes. Overhead, so overhead in this case means any other kind of redistribution or splitting of nodes, which is negligible in this case. For the real-time applications, we have structured data organization, that is B tree indexes arrange data in a hierarchical manner, facilitating quick searches, range queries, and sorting operations. Adaptability to multidimensional data. B trees are adapted to handling multidimensional data commonly encountered in data warehousing scenarios. So basically, whenever we encounter large amounts of data, we use B trees. This is all about B trees as of now. Let me hand over KD trees to Aishwarya now.
Okay, so my name is Aishwarya and I'll be talking about KD trees. KD trees or K-dimensional trees are a type of space partitioning data structure used for organizing data in K-dimensional space. So this will depend on the dimension. It works similar to binary search trees, but it has an additional parameter called dimension. So if you give 2, it'll be X and Y. If you give 3, it'll be X, Y, Z, and so on. Then KD trees, it consists of data, and you can split the nodes into right, left, and it'll have the data. Then the key operations we have done for the KD tree include insertion, deletion, search, and display. So for implementation of KD trees, we have additional to the functions, we have also used many helper functions. First to insert. So for insertion, we have a function which creates a node. So this will initialize the left and right child to null and it'll return the newly created node. Additional to that, we have an insert helper function. So this insert helper function, if the current node is null, it'll create a new node and it'll calculate the axis. So the axis will be calculated and alternated. So first time when you're inserting, it'll be x axis and next one will be y and then followed by x and so on. And then we have a compare array function, which it compares across to the elements of the array, and if they are not equal, it'll return a false. Now we have an sleeve function. This function basically returns true if both the left and right child pointers are null, indicating that it's a leaf node. Now we have a find minimum data. So this basically is used to recursively find the left node, like the leftmost node, and it'll return it. And then we have the delete. So the delete function, it has multiple cases. So the first case, if the node is a leaf, then you directly delete it. If the node has only one child, which is the left child, then you replace it with the left child. And the node has a right child, then you replace it with the right child. If the node has both left and right child, you have to replace it with the minimum value from the right subtree. So for this, you need to find the in order successor, and we have done it recursively. Next, we have the search function, and then after search, we have the 2D display function. So the 2D display is how is shown as the picture shows. So here you can see this is how our display function works, and this is how a KD also works, and it has two dimensions. This is an example for a two-dimensional KD, which has x and y axis. And talking about the time complexity of KD trees, the most of the functions of KD trees have a time complexity of O of log n. But however, in case of a skewed tree, which means that it'll get constantly inserted in the right or constantly get inserted in the left, it's either a right or a left skewed tree that will have a time complexity of O of n. And the display function again has a time complexity of O of n. The space complexity for KD trees. So the space complexity basically is O of n into the dimension, whatever the user gives. So depending on the dimension, the space complexity will vary for each of the given trees. Then we have the real life applications of KD trees. KD trees is used widely in a machine learning algorithm called KNN or K nearest neighbors. So where you have to find the shortest distance between like the points which are clustered. Apart from that, KD trees are also used in computer graphics, spatial data processing, and etc. Now I'd like to hand it over.
So, for the conclusion, the enduring importance of B trees and KD trees in the upcoming data science industry and data industry. So, as we know, the world is growing, and hence the data and data science industries are also growing. So, B trees and KD trees have proven to be invaluable data structures enabling efficient storage, retrieval, and processing of data in a wide range of applications. By understanding the underlying applications and principles and use cases, the developers and researchers can leverage these tools to build more robust and scalable systems, pushing the boundaries of what's possible in the world of data management and beyond. And the contributions were done by Aditya Srivatsan, Kusumita, Jayant, Hia, Nandita, Hashita for the development part. The testers were Nandana, Kanishka, and Aishwarya. The project manager was Ashwati, and the business analyst was myself, Anish Priyan. Thank you for hearing to this presentation. Thank you.